class, so this is for SDLs 3 and 4, linearization, how to linearize this particular one, and understanding what it means. So this is SDL 3 or 4, it honestly doesn't matter. You'll notice they look very similar. So all of this should be the same. In fact, you really should be at this part. So you should have made an XT graph with whatever data you had. If you did, you probably got some points. That look like this, hopefully, because you'll see that if you look at what kind of shape they make, it is parabolic, so it looks like a parabola, which is good because that's what it should. And we want to think about it in the sense that this is x equals x naught plus v naught t plus 1/2 a t squared, and that we know that the x naught is 0, the initial velocity is 0, so simplify this is equals x equals 1/2 a t squared. So this may or may not look familiar to you, hopefully it does, but also I want to draw you to the idea that this looks really similar to this, y equals x squared. So really our graphs and why we have specific shaped graphs is not random. They're meant to mirror things that we do see in physics and in real life. So you can see that this x is a lot like the t squared, this x is like this y, and all this is would say if I had a number here, because ultimately the acceleration is going to be a number when you find it, and that's all it is. It just helps tell you the slope. So if you could figure out the curvature of that line, you could figure out A. Do you know how to find the curvature of that line? Without calculus, you don't. So we're going to move on. The way we're going to move on is this. It's something that's called linearization. Hopefully when you heard linearization, you heard the word linear in there. Ization is the cause, so realization is when you realize something. Linearization is when you make something linear. And the way we're going to do that is by making a distance and t squared graph. Because, as your algebra teacher would have told you, maybe you forgot, this is a line. And I realize that's a little light, so I'll darken it. Y equals mx plus b is your basic line, where this is your y, this is your x, this is your slope, and this is your intercept, your y-intercept to be specific. So this is your x-axis, this is your y-axis. So we want to make this into a line. So we want to make it look like y equals mx plus b. So we're going to do some substitution. To do that, I am going to clear it. So if you need to pause and write what we have so far, please do so. Alright, so I rewrote our basic line formula and what we had for our x. So we want to make this. So we want to turn it into. I realize I wrote that backwards. We need to turn it into that. Well, how? So you'll notice there's no plus here. So really all that means that this is plus 0. So we don't care, but if it helps you to think about it, that's the way you do it. You can hopefully see the parallels between our y and our x. So y is x, there's really nothing to change. Our slope is everything that's in front of our other variable. So our m is both of these. Because really, all it is a number. We don't know what each number is yet, but we do know that much. That leaves us to something that may sound less intuitive to you, which is the only thing left is our x. So our x is going to be t squared. So this is why on that second page I say graph a x t squared graph. Because this is how you linearize it. If you make this your x-axis, because all this stands for is what axis it is. It doesn't have to be x or named x. So this is t squared becomes your x-axis. If it doesn't quite make sense, that's alright. Let me walk you through how to do it. So again, I'm going to erase everything, so pause it if you still need to copy it down, or you can rewind me and go back and listen. Alright, so I just wanted to pull up the instructions. So let's say these are your original values. I'm just making them up. So let's say you had x and your t measured, which you should have, and hopefully you got 0, 0, even if it wasn't in your data, but that is true. We also have, a lot of you guys did 0.5, 1.5, 1.0, 1.5, and 2. And you would have had some times to go along with those. So here we have our data. So this is how you would make your original, and this would end up being like a parabola. I'm not going to graph it. Hopefully you have something similar. Then you want to create a new table for yourself. So you want to add a section to your table. This section to your table is going to be the t squared, and literally all you're going to do is take all of these numbers and square them. So 0 squared is still 0. This becomes 0.64. 1 squared is 0.64. 1 squared is still just 1. 1.4 squared is 1.96. 1.6 squared is 2.56. And then you're going to relabel your graph so that it goes from 0 to about 3 and upwards of still just to 2.0. So I'm going to go ahead and use the graph paper on mine because it's much neater. So to graph, remember, first things first, you need to have some clear axes. Make sure you always label. So this is t squared, which means this unit is second squared. This is still x, or position, which means it's in meters. And then we want to graph this. So this should go up to 2. So it looks like we're going to go, this is 0, 0.5, 1, 1.5, and 2. This needs to go up a 2 as well. We have a little more room to work with, which is good. Alright, and hopefully these are going to go by 0.2, but because I'm running out of space, I like to try to write smaller. I'm going to skip some. So I'm still counting by 0.2, but I just don't have the room to write each little one. So I'm essentially skipping to counting by 0.4. Alright, so now I need to plot them. So my first point is 0, 0, and I'm going to plot in a different color to hopefully make it easier to see. My first point is 0, 0. My next point is 0.64. So it's not quite 7, which would be in the middle, so it's closer to the 6, and it's at 0.5. Alright, then we want to do at 1, it's 1, which is nice and convenient. Then we want to do later 1.96, which is pretty much 2, and 1.5. Then we want to do 2.56. Just close to 2.6, just at that point in the middle. Except a little closer. So you notice it's definitely not a parabola, and since our goal is to linearize, hopefully you can see that that is quite close to a straight line. So if we were to do a line of best fit, not the best one, a little too low. You'll notice I didn't actually hit any points, and that's actually best. You don't want to hit points because then you start to make it look like that just because, not necessarily for any reason more than that, but just because you think it should look like that, and that's exactly what you want to avoid. So now we have a line. So what does this slope mean? So remember with our linearization, we said that x equals 1/2 at squared. That means if this is my x, this is my y-axis, this is my m. So the slope of this line is equal to 1/2 a, which sort of makes sense if you look at the idea that we have an m, we have an s squared, and remember, meters per second squared, that's an acceleration. So the question on this was find the slope and then explain why it's really, really close. So before we even find it, hopefully you're starting to see why it's really, really close is because that was the slope of our line. So as far to how do we find the slope from a line, remember we need to pick a point. In fact, we want to pick a point that's not exactly anywhere. In fact, this is a really nice one right here. It crosses at 2.8, so my final point is 0, 0. In the x direction, it's at 2.8. My total rise is right in the middle of between 2 and 2.5. So that means it's at 2.25. So we can find the slope of our line from this. And we get 0.8 meters per second squared. And so remember, this is the slope. So it's not our exact acceleration, but it is very, 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 very close. So again, just to give you a visual, this is our x over our t squared. And I'm going to erase this. And since if we then solve this for a, so by solve for a, I mean, too thick. X equal to 1/2 a t squared. So move everything else over. So it means 2 on top, t squared on bottom. These cancel. We get 2x over t squared equals a. So you can see there's some strong similarity right here between these two terms. They're really, really similar. In fact, the only thing we have to do is we could take our slope and plug it in, because remember, the slope is half of the acceleration. So if this is half of the acceleration, how do we get the whole acceleration? We multiply it by 2. So we can essentially plug this in here, or you can even just set your slope equal to 1/2 a, and you'll see that, the only way to get that is to multiply by 2 on both sides. If we do that, sorry, it's getting a little crowded here at the bottom, we get 1.6 meters per second squared as our slope. Will this be your slope? Maybe, maybe not, depends on your numbers. If your numbers pop up, if my numbers pop up on your lab, you're not going to get points for it. So I want you to do these with your numbers. Yes, I know it's a lot of work. Yes, it is still good for you. Hopefully that extra day today you had to work on this helped. Make sure when you finish this, you must justify. If you do not justify, I'm not going to give you credit for it. It's an all or nothing. I'll just hand it back to you and say, finish it. So if you need help on the justify, you can listen to it. Please do not copy me down exactly. It's one of the reasons why I didn't write anything. Hopefully you are listening. If you aren't listening to this video, it's not very helpful. If you are listening, I'm not going to grade this as homework. So you don't have to show it to me tomorrow. But if you have it, you should be able to go on now and finish your labs, which are due at the beginning of class tomorrow. Alright, I will see you guys tomorrow. Good luck.